Welcome back. We're still talking about RISC-V assembly language, but we're going to take a bit of a detour to see what is happening with that assembly program once it is written. So say that we have two pieces of assembly code, foo.s and bar.s, which are our assembler source files, which are written in plain text. We're going to pass them through the assembler, which will produce machine code object files, foo.o and bar.o. Those extensions .o stand for the object files. We may have pre-built object file libraries like lib.o that may contain some commonly used functions, like, for example, a division. Linker will take our object files and the library files and link them together. What is linking them together? We'll place the addresses in appropriate spaces and put everything together such that it looks like one piece of a program. The output is a.out, which is machine code executable file. So where does that machine code executable file live? It is not small enough to fit in the register, so therefore it has to live in the memory. Remember, our memory is big and is byte addressable. However, these bytes are put together to form 32-bit words. We'll have a section of memory where the data will live, and then there will be a section of a memory where the program will reside. Those are typically kept separate from each other, with an exception in 61C exams, where data tends to run on top of a program and causes interesting effects over there. But in practice, that usually doesn't happen. So we got a pretty good idea of how does the program look like now. It is essentially a sequence of RISC-V instructions, where each of these RISC-V instructions is 32 bits wide. And we will be executing them typically in order until we run into one of those that corresponds to a branch or a jump, and then we are going to perhaps jump to another place in memory, to a different address in memory. What does the processor do with this program? Well, this is a picture that we hopefully have had tattooed already. So our processor to the left has a control unit and a data path, and then memory is to the right. Inside the processor, inside the data path, there is one very special register, which is called the program counter. Program counter is internal to the processor, and it holds the byte address of the next instruction that is going to be executed. So it is something that is really important. A control unit is going to use the program counter to produce and to fetch the instruction from the memory, take a look at what is that instruction, and execute it by using the data path and the memory system. And then we'll update the program counter to point to the next instruction that is going to be executed. Most commonly, that will be the next instruction in sequence, but sometimes it may be a branch. The next instruction in sequence is 4 bytes away. You have to keep that in mind. It is 1 word away, but that is 4 bytes. So in order to point to the next address, we need to increment the program counter by 4 bytes. Or to load into a program counter a new address if it is a branch. Hopefully you got now a reasonable picture of how does the processor execute a program. It may be helpful understanding what comes next. In the meantime, a few other interesting things that will help us, or helpful things that will help us understand how to work through the functions later on. First, there is something that are called symbolic register names. There are 32 registers in RISC-V architecture. The first one is reserved to be a 0, but the other 31 are assignable. But some of them are going to have very special purposes, and it will be kind of hard to remember which one does which out of 31 of them, so we give them symbolic names. For example, physical registers x10 to x17 have symbolic names A to A0 to A7 for argument registers for function calls. Or 0 is spelled out as a symbolic name for a register X0. There is another useful thing, which are pseudo instructions. Remember, RISC-V does not have many instructions, and some of them look fairly cryptic. Although we can do things in just a simple one instruction, it looks cryptic. For example, if we want to copy a value of one register to another, we have to do add immediate of a source to a destination register with an immediate value of 0. Other processors may have an instruction move. So in this case, move instruction is a symbolic instruction that corresponds to add immediate with a 0. So move, the destination register source register, is the same as add immediate destination register source register 0. It copies the contents of a source register to the destination register. The other one that we'll find useful is load immediate. Although it does not work with the memory, it simply loads an immediate value into a register if it is a short immediate that can fit as an argument of an add immediate. And finally, a common instruction that we will run frequently in a code is no operation, or it stands as NOP. That's when processor needs to wait for something, for example, for a datum to come from the memory. It is spinning around and doing nothing. That's a NOP. Well, NOP is anything that uses X0 as the destination register. So X0, X0, 0, add immediate X0, X0, 0 is a good NOP. These instructions don't change anything in the way how they're being executed. They just make the code more readable. So instead of trying to figure out what does add immediate our destination our source 0 do, we just write a move. That's it for now. See you in a bit.